Thank you very much, and good morning, everybody. I'm glad you made it early. So I put my take-home message right there. So in case you want to check in your early morning emails during my talk, that's what you really should remember, that when we are able to get samples from really the lower part of thick mass transport deposits, cores, and the ways how we can analyze cores actually do reveal a lot of insights that we can use, and we're just starting to understand how we can use this strain and get to the dynamics of large submarine landslides. And I mean, what many of us know, and what we are pretty good at, is surveying the seafloor in really high resolution. We can map landslides, and we can get a lot of properties from the seafloor, and we have 3D seismic data available, so we can look into the subsurface, we can map geometries, and we can deduce amplitude, anomalies, and so on. So we can do a lot, and we have a lot of knowledge from theoretical model, numerical model. But what we really do need in order to advance is particularly how often do landslides occur. So we need to somehow get a frequency, so we need sample to date events, and in particularly we need samples from the relevant intervals within landslides to actually deduce the dynamic that we can come up with consideration for what's the tsunamigenic potential of a landslide. And that ties into this session today. And my contribution to this is I will talk about a large project that has been going on over something like the last 4 years, where we were integrated ocean drilling program project that investigated the Nankai Trough submarine landslide history. And you see an overview. We are in southwest Japan, where the Philippine sea plate here is being subducted below the Japan arc, forms this huge accretionary prism, and on that upper slope of that accretionary prism here, there are a bunch of small, and I'll zoom in, they're not that small, but on this scale they do look small, trench slope basins that are filled in by landslides over the last 2 million years or so. And overall, this is tied into a bigger project, Nankai Trough seismogenic zone experiment with using the drill ship Chikyu from the Japanese. And so I'm going to zoom in now. So you see there's a bunch of boreholes that allow, and there's a 3D seismic survey around here. So we're going to zoom in that area to try to address these kind of two fundamental questions. But I will focus on the dynamic aspects of it today. So this is a zoom in, again, this kind of 3D reconstructions. There's a kind of a steeper slope in the hanging wall of an out-of-sequence thrust. You can see that in the seismic here. And this is the slope basin, something like a kilometer of sediments in here. And a little Pleistocene to Holocene sequence with mappable mass transport deposits, and particular one, huge one here, it's just the base in red, and this pink horizon, the top of it, a larger mass transport complex up to 160 meter in thickness, and we got 2 sides drilled, both sides, continuous coring down to something like 300 meter, and also both sides with logging while drilling. And I'm gonna show you some of the data here. This is basically already kind of the summary of all data available. When we do the core log seismic integration, you see here data from the logs, resistivity, natural gamma. This is the seismic section from the 3D data cube that has been acquired. And this is the compiled lithostratigraphic column, and what we are interested in are these gray bars. Those are the thick landslide deposits that we were trying to understand by doing this experiment. And then also here there's the bedding tips picked on resistivity logs. So by logging while drilling we can get geometrical analysis, and I'll come back to that, what we can learn from this. And we have 2 sites, and obviously I cannot summarize all of this, so I just kind of give you, like the next couple of minutes, a few highlights on this. I zoom into this one site, CO18, where we have something like 300 meter here. a bunch of stratigraphical age-constrained biostratigraphy, tephra chronology, so we can analyze the frequency of occurrence. And you can't read the number, but basically it's like something like 1 million year worth of landslide history at that site, and we got something like 6 larger events occurring in this 1 million year. And there's, as IODP, a lot of data is being produced on ship and in post-cruise work, and just plot here's the bedding peaks, porosity, and the strengths, and interestingly, and I'll come back to this, on the base of this thick MTD, there's kind of a reversal in the strength profile, which I come back later. And here, just some nice pictures on how the cores look like from MTDs. So in really summary, the key finding so far is that actually something like 50% of the whole stratigraphic section is worth of remobilized mass transfer. This is interesting also in terms of mass transfer, so which is not so much the question of our geohazard session today. And interestingly, like initially we went there to kind of say, well, this is an earthquake area. There must be a lot of landslides because there are a lot of earthquakes. But actually what we find is the order of recurrence is like the recurrence interval is 2 orders of magnitude lower than actually the earthquake cycle. So we are now looking into preconditioning factors such as climate that are possibly important. What we also find is there's a sand layer, a really coarse sand layer, and Sassa and colleagues have done some dynamic ring shear analysis to show that the material actually is capable of having accelerated motion upon liquefaction, upon earthquake, seismic shaking. So this ties in. But what I really would like to focus in my talk here is now to this, so to look at like go into the microscale of cores that we have available to actually study or try to develop a proxy that we can somehow then, and I'm not yet there, but I mean, this is a great community, we can build on this, somehow invert from the stratigraphic record into the dynamics of landslides and learn something from there. So let's see how this evolves. I show you again this movie as on my first slide. It's basically a X-ray computed tomography as this has been done in medical CT, and these are just 3, this kind of the typical core section we are used to look at, and we would have a really hard time to actually pick that this is a sheared and like the lower part of a landslide, and only if we are able to actually look into the structure in 3D, we do start to see something like folds in this, or here we have higher CT numbers. So below is an undeformed section, and here is really high density. We interpret this as being the sheared base, and then kind of going into the more chaotic. And if you have realized, maybe if you look at these red dots there, they're dots and lines and dots and lines. So if you think this in 3D, those high CT specs, they're somehow aligned. And when we first thought at it, and also kind of looking at other proxies, and I will show some of them, they seem to be aligned in terms on the shear direction. So we were interested in what are those high CT specs that are aligned within the shear distance of a basal thick landslide. And we found those to be bioturbation tubes. And when we looked them under the scanning electron microscopy, we found those small crystals here, and we also did some electric dispersive spectra to see the chemical components of it, and we found those are so these are the clays that are kind of coated around of it, and then we have some iron and sulfide inside these tubes here. And we did some XRD, and we found those to be marcasite and pyrite, which kind of nicely fits into that, so the interpretation of worm tubes that where when worms are digging around the sediment and eat, and they eventually digest things, it's high organic content, and if they get buried, there is a transition from organic material being pigmented by iron sulfide, eventually makes its way into pyrite. And interestingly, the pyrite is a paramagnetic mineral, and which is capable of kind of getting some higher magnetic susceptibilities. And there's a nice, oh, sorry, I thought another slide is coming. So just briefly go back. Using these this indicator for deformation, we then can go into the whole, all the cores. So this is the core through the thickest of this 60-meter worth of one mass transport deposit, and do a detailed structural analysis. This is work by Gianandrea Pini, and you basically see this is just a zoom in from one section. This would be the core, and he did looked at all this CT analysis and did a structural interpretation on the core. And what we basically can see, it's hard to see because it's not zoomed in, but there is a lot of deformation like this, folding, and in the lower part shearing, and these violet colors here, those are debrides. So we basically start to be able, by core, to distinguish like internally deformed sediment, sheared sediment, folded sediment, and above the debride, this kind of, and that's what makes up the seismic image. So here comes the magnetic susceptibility study I was mentioned before. Kanamatsu-san and colleagues, they collected small cubes on the core and analyzed how the magnetic susceptibility in space is oriented. So if one direction shows a higher magnetic susceptibility than another, we can somehow infer the ellipse of how these grains that have higher magnetic susceptibility may be oriented in space. And he kind of finds like oblate structure, which just means this is compaction. But if we go down at the base of landslides, like here, the MTD5, we see this triaxial shape, which indicate that the grains that are carrying the magnetic signature are somehow aligned. So we can use this then by doing like paleomagnetic reconstruction in time and space. We can even use this to deduce flow direction on the landslide from a core sample by looking at these microstructures. And Kanamatsu-san then came up with this interpretation, and he also saw that by having the orientation, we can even kind of get to these folds within an internal mass transport deposit and see the high shear component down here. So having said this, this is really kind of the microstructure scale. Those are small minerals that carry a signal which we can use to get into the deformation. And having learned about this, we can kind of zoom back and now look at logging data, which is an industry kind of that's easy available. Coring always is a little bit more of an effort, but logging might be easier available. So we're looking here at azimuthal resistivity across this MTD6 here, and those are the TET plots of all the bedding peaks. So on the left-hand side, it would be kind of flat-laying strata. On the right hand, it would be steep dipping strata, and the direction of the TET plot give you the direction of the inclined plane. And you know, when we start to look here, we see something like 10 meter worth of more or less steeply dipping in the same direction, then a kind of a slight curve. So also from logging data, when we know what we are looking at, we start to see slump folds and all these kind of things. And in the upper part, it gets more chaotic. And so this is kind of an important thing that we can start to look at logging data. And then if we upscale from this microscale structure in the core to the logging while drilling and into the seismic section, we can start to, obviously the resolution here is much lower because those are like a wiggle here is worth something like 20 meters, so if I have it right in my mind. But from this knowledge from core, we can learn more about the seismic scale. And I guess that's my conclusion here, that we actually do have these bioturbation tubes in MTD that we can use as new proxy of strain, and we can use this and develop techniques now that allow us to calibrate the structural and rheological interpretation on seismic data scale. And so far, what we learned from this particular landslide is that our data hint at accelerated motion and high mobility of this landslide, yet at least the lower 40 meters or so seem to not really disintegrate, but move en bloc. And these two ingredients hint at the high tsunamogenic potential for this kind of landslide we've been studying there. Thank you very much.